In our last unit, what we want to explore are our aromatic rings. So before we get into those, first, our nomenclature slide. This is the big one that covered everything. But the point that I really want to draw you to is in the lower left-hand corner. Where's aromatic? Aromatic isn't on our list of functional groups. And that's really just because what the aromatic ring is kind of a substituent. Okay? It can be a main chain because it's long enough, so like a cyclic structure, it could work. But because it has those double bonds in there and that special chemistry that was addressed in that PlayPosit video about aromaticity, it gets a new name, and that's where we encounter benzene. We could also call it by another name, which I'll just say here in just a little bit. Okay, so if we go through and look at our first example, well, the core name in this case is benzene because, well, we have that six-membered ring with the double bonds, alternating double bonds. We also have a chloro substituent, so we could call it chlorobenzene. Okay, and for those of you saying, well, that seems really straightforward and simple, well, let's just move to the next one. We still have that benzene. Now, NO2, hopefully we remember, is actually a nitro, and this becomes nitrobenzene. And for those of you being like, well, when does it get difficult? It doesn't really. Okay, our nomenclature is probably one of the most straightforward things when it comes to benzene rings. We do encounter ring issues that we saw back with cyclic structures way back a long time ago in Unit 1 with assigning priorities with multiple substituents. But for the most part, it isn't anything new. Okay, it's pretty straightforward. I will say that you can see benzene show up by another name. So benzene would be kind of a common name that has been converted into IUPAC. That's like what all of our functional groups are. So if we go through and look at the official IUPAC, I guess, or strict rule broken out name, rare to see, but we could possibly pick it up. We've got a cyclohexane, or sorry, a cyclohex, but then it's an ene, but there's three of them, so cyclohex, triene, and then we should really specify where each of them would be located, and we'd get 1, 3, 5. So you could see benzene written as a cyclohex 1,3,5 triene. This is why we call it benzene. Right? So again, the rules are there. It's just about kind of applying them. This summarizes all of our rules. It's a summary, not the exact answer. Right? When it comes to nomenclature, the exact answer is what somebody says it is, and that's the way it is. Okay? We do encounter kind of a not IUPAC naming system. If we think back to our alkenes, we had cis and trans, and those weren't IUPAC. Okay? So we're going to use IUPAC rules. Cis and trans had to be E and Z. Okay? So we had to specify those as Z and E respectively. Okay? Well, aromatic rings are going to encounter something similar. Okay? But that's going to happen when we have multiple things. Just like with the double bond, we needed two pieces to reference. If we look at the structure drawn here, that chlorine, well, there's only one thing. We just have that chlorine. It would be by definition at position 1. Well, what if I add another thing? Let's go through and put in a bromine. Let's not put in a bromine because that math or alphabetically is going to be problematic. Let's put in a methyl, a CH3. Okay, chlorine comes before methyl, so C comes before M. So we would put this as position 2. Note we're counting counterclockwise. That's clockwise, actually, for the record. You could just as easily have put it up top. Okay, and now the nomenclature is still 1, 2. So the numbering just goes to get the lowest numbering. This referencing of the 2's could theoretically get confusing for some people, anybody that is numerically challenged. So what we might try and do is come up with a name for it. And ultimately 2 is a name, but we want to get creative and reference that name. So if we're looking at that 2 position relative to the chlorine, okay, it's 1 bond away, we could reference this as ortho. One of the potential advantages that comes out of this is that if I continued to number around the ring, what you might notice, particularly how I'm coloring, is that you get some equivalent positions, okay, which should be something you remember from spectroscopy. Okay? The 2 and the 6 position, if I put CH3s at both those positions, those CH3s are equivalent because of symmetry through the middle of the structure. Okay? The other thing that makes that nice is I could say, well, it's di-substituted, as in there's 2 methyls. It's a di-substituted chlorobenzene. I guess tri-substituted if we're really going to nail that down, with 2 methyls. Those 2 methyls are at the ortho position. Right? Or I could say those 2 methyls are at the 2 and 6 position. Ortho is sort of shorter than saying 2 and 6. Okay? So there might be an argument for length of term. So the referencing of that position based off of the name can be a little bit easier to nuance than based off of the number. If we had more substituents on there, the ortho reference might be easier than the numbering, because then the numbering you would have to nail down the exact numbering positions. You'd actually have to draw out the structure. So the ortho name can be beneficial. If we continue around and add something at the 3 or 5 positions, you'll again notice that line of symmetry on our structure, and that will get called the meta position. Okay? And then the last one at the complete opposite would be the para. Okay? And so one of the things that can come out of this that gets potentially confusing is what are those ortho, meta, and paras in reference to? Well, the same thing happens with our cis and trans. I could look at a cis and trans double bond, and you might go through and call that one cis. Well, I'm going to say the hydrogen is trans to the methyl. Okay. It is. I'm allowed to say that because cis and trans don't force a nomenclature rule on it. It's the relationship between any 2 groups. The same thing is going back to our ortho, meta, and para. They're all relative to our primary functional group. Okay? That primary functional group could be whatever you want it to be. Okay? So this is why you have to be very careful when using ortho, meta, and para to make sure that you know where that focal point is that allows that description. Okay? Why would I mention this? Well, let's go through and see what happens if we switch to a slightly different orientation of the molecule. Okay? And we'll introduce another interesting piece here. Remember symmetry. We could go through and call this ortho, meta, and para, which is an awful lot of letters. Okay, so of course we decided to abbreviate. Para, for the record, just in case you were wondering, starts with P, not with M. Okay, so OMP. If we now move to this rotated structure, what I will sometimes get students saying, well, is O, M, and P. And so what you've done is locked the OM and P relative to their starting location, which is irrelevant. It's always relative to that primary functional group. In this case, that primary functional group is the only functional group on that structure, which is that chlorine. That's based off of where everything is referencing. So ortho, meta, and para. Okay? So I want you to be familiar with that terminology because we will use that terminology when referencing multi-substituted reactions, and we'll see that in 4 or 5 videos probably. Okay. The other thing that pops up is there are lots of common names for benzenes. Okay, so for some compounds, there's just a common name because it's been around so long. That common name can become the parent, and it's looking like, okay, there it goes. What we've got here are a bunch of substituted benzenes. They each have a functional group connected to it. Well, that is such a common kind of functional system. The piece that's added and the benzene interact in such a way that we give it a name. Okay? very borderline on deciding whether or not you should have those names memorized. I wish I could not hem and haw on it, but I would bet those three for sure you would see pop up. Benzoic acid you've seen show up. Okay, so you should kind of commit those to memory. When it comes to exam 3, have it on a cheat sheet so that you don't have to really slam that memorization in right away. Okay, how does this go through and apply? Well, our all too fun compound TNT stands for tri-nitrotoluene. So what we're doing is taking the base, a common structure of toluene, and we are adding 3 nitros to it. For those of you wondering about the placement of where I've put those nitros, because there's a couple different orientations we could do tri-nitrotoluene, right? Some of that has to do with the chemistry that I'm aware of that we'll see a little bit later in the unit. The name itself doesn't really tell you that it is 2,4,6 trinitrotoluene, because 2,4,6 would just be painful to list out. Okay, that was probably part of the name, and people just dropped it off because it was too difficult. Okay, but trinitrotoluene is in reference to that aspect. Okay, so you got that core structure. Next part is our spectroscopy when we're looking at our aromatic compounds, and so we'll walk through this a little bit slower because I've been seeing some people struggle with spectroscopy. First and foremost, know what you're looking at. So we should be looking at a structure. Let's just pick a standard aromatic structure. We'll pick benzene. Okay, what IR gives you are bond vibrations. So that when we look at benzene, what you should be telling me is carbon-carbon double bond, carbon-hydrogen, sp2, and you might throw in a carbon-carbon single bond. The carbon-carbon single bond you can pretty much eliminate right away because that shows up deep in the fingerprint region. So really when we're talking about aromatics, we get 2 signals that we should be looking for, the carbon-carbon double bond and the carbon-hydrogen sp2. Okay? It is a little bit more complicated than that, and we can see that in the image to the left. Okay? If we started off that 3000 to 3100, that's our carbon-hydrogen sp2. Okay? And then we see this 1415 to 1650 is our carbon-carbon double bond. You'll note that we also have some patternings within 1700 and 2000, and you might be like, well, why didn't you talk about those? They're very weak, okay? They're so weak that sometimes we don't see them at all. Sometimes they stand out and they're really obvious and you can use some information from it. Usually not. And then the last 2 are deep in the fingerprint region, which usually means it's too difficult to analyze. That's why when we talk about our aromatics, what we should be referencing are those bonds, the CHsp2 and the carbon-carbon double bond. Okay? Those 2 are decent tip-off that we're looking at an aromatic. It could just as easily be an alkene as well. So how do you differentiate the alkene? If we look in that 1450 to 1650, you usually see a couple signals pop up there. It's a challenging one to nuance, and I wouldn't push that too hard. IR should be a fast analysis. CHsp2's carbon-carbon double bond. Oh, I have more evidence that tells me it's an aromatic ring. Those signals were due to an aromatic ring. Okay, but they came from the individual bonds, so that's important. So that's kind of the standard. The lesser known signals. So if we look here, we're looking at that 900 to 700 range, and on the far right, we're looking at the 2000 to 1667. Okay, that's those 2 ranges that were challenging to nuance. And if you look at it, it's not just there's a peak, there's certain patternings that go along with them. Okay, these are sometimes present and can be useful. I don't want to spend a whole lot of time looking at it, but really what we're saying is that if we had, say, this structure mono-substituted, we would expect in the IR a strong signal about 750 and a strong signal about 700. Okay, that black one being a really characteristic signal to pop up. Right? If for some reason we had it dye substituted, well, now we have ortho, meta, and para. And if you take a look at those ranges, they change a little bit. Okay, this is deep in the fingerprint region, so it could be a bit challenging to nuance. But if that's what you're stuck with, that's what you could do. You'll never be stuck with it. Okay, I just want you to be aware of it. Same deal goes out to that 2000 to 1700 range ballpark. You get very particular patternings, okay? And that's what this diagram is trying to show. We're trying to see those patterns and what they look like. So we're getting 4 peaks. We're getting kind of 3 weirdish looking peaks. We're getting 2 peaks a little bit away, 2 peaks kind of overlapping. And that corresponds to those individual patterns, okay? Some of them are really difficult to differentiate. For instance, if we take a look at that bottom, are you really going to tell me that you can tell a difference between those? Okay, that's going to be a challenge to nail down. Okay, but the information is there. You could go after it. When we move to NMR, aromatic rings are fantastic because a signal in the HNMR, which I'm officially not looking at yet, tells you you have an aromatic ring, which gives you a lot of atoms nailed down. Carbon NMR gets a little bit dodgy because the alkene moves into that range sometimes too, with a little bit of resonance. But if you're seeing a bunch of signals in this 100 to 150, it's probably not just an alkene. You're probably looking at an aromatic. And that multiple sequence of signals tips you off to it. So it would be kind of a large amount of signals in that range. It's a bit dodgy of an analysis, but it could work. The other thing that's nice with it is that if you have an aromatic ring, it's got six-fold symmetry. Oof, not when I draw it. 1, 2, 3, 4, 5, 6. There's so much symmetry within that structure. For those of you looking, we're going through atoms and we're going through bonds. Okay, if you're freaking out at my dotted lines. Okay, there's so much symmetry within that means there's a lot of identical carbons. So that's going to reduce the number of signals that you would see. So you could go to tables that are kind of shown here, and you'd be like, oh, I see 2 signals in that range. That must mean it's this dye substituted where the 2 things that are substituted are identical. That's a pretty big conclusion to draw with just 2 signals. That's cool. I see 3 signals. Right? Well, then that means it's dye substituted. Again, same things. I see 4 signals. Oh, that means it's para substituted. They're on opposite sides. Well, is it? Is that the only way you get 4 signals? What they're showing here is you could get 4 signals with 3 different structures. Okay, so be a little bit careful in just full on saying, oh, well, it means this. It doesn't necessarily mean it. It's a bit of evidence that leads you in that direction. You have to take in the whole picture, okay? And in most cases with our exams, that whole picture is your multiple choice answers. Make sure your multiple choice answers align to it as best as possible, okay? The next one, HNMR. HNMR, I would argue, is even better than carbon NMR because in HNMR, the hydrogens for the aromatic show up about 7 to 8. You can sometimes see alkenes shifting in there, but it's usually pretty rare. You're looking in that 7 to 8 range, which means you see a signal, aromatic, done. Draw it, okay? And now interpret. Okay, well, what should you interpret? Well, if you have a benzene, there's 6 hydrogens around it. Okay, it's probably not just benzene, for the record. So there's probably something substituted on it. As soon as you substitute something on it, those hydrogens are no longer identical to each other. And you could now pick that out of the integration pattern. So how many hydrogens per signal? And that can help you analyze it. Okay? One of the biggest, most characteristic things is this para substitution that we're seeing down below. Because we're looking at HNMR, it probably makes sense to go ahead and draw on our hydrogens. Oh, and let's not give away any pieces yet. We've got those 4 hydrogens. So first off, we should see that there's that line of symmetry through there. which means purple is red. They're identical, okay? And green is blue. They're identical as well. So that helps us out. Do we have a line of symmetry? And because I got rid of green and purple, do I have a line of symmetry here? Okay, we'll know because we're looking at bromine versus nitro. That means the red hydrogens and the blue hydrogens are different from each other. So based off of this, I should expect two signals. Okay, I should get a red signal, which is dumb, but I'm just going to do it this way, and a blue signal, if we will. Okay, the next part, how many hydrogens are represented by the red signal? Well, there's two. How many by the blue? Well, there's two. Integration is a ratio, and so that could very likely boil down into a 1-to-1 ratio. That's okay. We could still draw conclusions from that. The next part, which is everybody's least favorite, okay, unless you've been doing lots of spectroscopy, and because then you can go through and you see multiplicity, which is in reference to the number of neighbors. That hydrogen has one neighbor, okay, which means the blue hydrogen with one neighbor turns into two peaks. The red hydrogen likewise has one neighbor, which then turns into two peaks. Two peaks is often referred to as a doublet, and this is a little pet peeve of mine. You will sometimes hear people reference and go, oh, it's the para-substitution, it's a doublet of doublets. No, it's not. It is two doublets. A doublet of doublets is a very particular splitting pattern that has to do way complex Unit 1 stuff, okay, or first semester stuff. Okay? This is two distinct doublets. A doublet of doublets is one signal. This is two signals. Okay, so please don't call it a doublet of doublets. But if we looked at our spectra in this 7 to 8 range, what we might expect would be two peaks about the same size, two peaks about the same size, and that right away screams para-substitution. So as soon as you see it, boom, there it is drawn. Now you've got those two pieces, okay? And that's pretty cool, okay? Last thing, because this is our first kind of intro slide, section of our slides, is that here's our big summary of everything. I do apologize that my picture's floating in there, and I'm gonna attempt to move it. Cool, that worked out okay, hopefully. And what we're looking at, sorry. We're looking at all of our reactions, okay? So this is everything within this unit. That isn't too bad if you consider that every other unit, it was probably multiple pages, okay? But if you wanna now be just like, I'm just gonna memorize, crank it out, good on you if you can do it, okay? It's probably not a horrible idea anyway. And we'll look at kind of those nuances on where it's going to be really important to actually have some application. Okay, but we've got EAS right over here, that direction. Okay, we have the description on multiple substitutions. So if I'm going to run a reaction and I have multiple hydrogens being substituted, the rules for that, I shouldn't use a white pen, are over here. Okay, we have to decide what that atom X is. What's our first substituent? Is it an activator or is it a deactivator? Okay, that's EAS. That covers everything. It's amazing. Okay, it's beautiful. Everything works beautifully. Resonance for the win. Okay, then at the very bottom, that just looks weird if you were here in person on what I'm pointing. Okay, but if we look that way on the screen, okay, we get the Birch reduction, which we kind of already talked about. And then we get two new or different weird mechanisms. One called the NAS, so nucleophilic aromatic substitution. EAS was electrophilic. And then an elimination addition reaction. So those are all of our reactions for this unit. This should have been a lot shorter of a video. I apologize. So with that, I think, yep, we're going to go ahead and stop. Floating head.